All right, so good morning or good afternoon, everybody, depending on where you're logging in from. I'm going to get started with the webinar, Exida's Pathway to Safe Machine Learning. Just so you know, when you're logged into the webinar, you're in listen-only mode, so you won't be able to speak, but you will be able to type in questions. And at the end of the presentation, I'll go through and answer the questions that have come up. So please type those in as we go along. All right, my name is Molly O'Brien. I'm a senior safety engineer at Exida, and we're going to be talking about safe machine learning today. So a little background about me. I have my PhD in computer science from Johns Hopkins University. There I did research in computer vision, deep learning, and some applications in surgical robotics. Now I work as a senior safety engineer at Exida, and I lead our safe machine learning research efforts and projects. I also perform hardware and software, functional safety assessments, FMEAs, and FMEDAs. I work on projects in the automotive, process, and semiconductor industries. What we're going to be talking about. So first we're going to talk about what's the problem with using machine learning in safety critical tasks. We'll talk about doing an ML process assessment, then an ML statistical analysis, and then how you can integrate an ML model that's been validated into a larger system. And then we'll have some conclusions at the end. So first, let's talk about the problem with machine learning and safety critical tasks. Now, if you're coming from a functional safety background, one of your first questions might be, why would you want to use machine learning at all in a safety critical task? You know, these models are complicated, it's challenging to predict how they're going to fail, and often they fail in unpredictable ways. So why use these at all? And the answer is generally that there are some problems that it's very difficult or impossible to solve without machine learning. Now, what types of problems am I talking about? Here, I group them into sort of two general categories. So one would be tasks where it's challenging to specify a complex task in all settings. So for example, let's take perception. Let's take pedestrian detection in an autonomous driving scenario. So if you were to try and do that without machine learning, you would need to hand code rules for what pedestrians look like or hand design filters. And this is what was done in computer vision, you know, largely before, let's say 2005, excluding sometimes in the 80s. And so what we found is it's very challenging to get a level of performance that's sufficient for practical tasks without machine learning in some tasks. So that's one reason why you might reach for machine learning. Another reason would be that it's challenging to find a parameterized or a closed form solution to a problem without machine learning. And so complex control problems can fall into this category. And one example of that would be, let's say, a robot grasping task. So in general, we're only going to use machine learning in a safety critical task if there's not a good alternative. Okay. And then how do we want to address unsafe machine learning? And I think in the news over the last couple of years, we've been seeing some examples of, you know, accidents and injuries that have happened with systems that have machine learning embedded. And so the question is, how can we use machine learning in a safe way? And in functional safety, the answer to that is we want to manage the risk of the machine learning. And so this risk is a measure of both the likelihood and the consequence of an adverse effect. And functional safety as a discipline has evolved to help manage risks in complex engineering systems. So first, let's talk about functional safety in other industries. There are a number of safety standards that certify hardware and software in a number of different industries. And in general, we can think of these standards as having a two-pronged approach. So the first piece is a process assessment for how the hardware and software were designed. This could encompass the safety life cycle. It's looking to ensure that there's been a correct implementation of the safety-related and the intended functionality of the system or subsystem. And it's trying to reduce systematic errors. So processes and procedures, how the design was done, how it was documented, how it was validated, all this is going to fall into a process assessment. And then the second piece is a quantitative hardware analysis that is used to calculate the probability of a dangerous failure. So typically this is going to be done with an FMEDA, and in the standards there are different metrics where you have to hit different levels. So typically there's some architectural requirements that might be your diagnostic coverage or your safe failure fraction if you're talking about IEC 61508. And then there's also a probability of dangerous failure that has to be met. And so by using these two prongs, you can mitigate risk throughout the entire engineering life cycle. And sometimes going through this assessment will lead to a certification of a product or a system. Now, exida is working on developing a scheme so that we're able to assess machine learning and mitigate the risk of machine learning when it's used in these types of safety critical tasks. So before we get into too much detail about what exida's approach is, let's talk a little bit about what the existing standards say about machine learning. So generally, the existing published standards were not written with certifying or assessing machine learning in mind. There are a number of working groups that are developing ML safety standards and different guidance. And in general, what exida is looking to do is assess with the existing standards whenever possible, but then also develop additional guidance because machine learning is going to introduce new challenges that aren't addressed with the existing standards. And here I've just included a brief summary of some of the places where machine learning is referenced in existing standards. So in the automotive industry, ISO 26262 is the functional safety standard. There's a reference to ML, and it talks about that trained weights would be considered configuration data in part 6. And this is the software portion of 26262. There's also a SOTIF, safety of the intended function standard in the automotive industry. This gives some insight for how you could apply machine learning in ISO 26262. And there's also an Annex D. It talks about some implications for machine learning in ISO 26262. Now in the process industry, IEC 61508, there's a mention in part 3, which is the software, that it prohibits using AI to generate test cases, but that's really all that's mentioned. So we're seeing some mention of machine learning, but there isn't really an approach of how you would assess and eventually certify the models. So let's first talk about what we're thinking for an ML process assessment. And for the assessment scheme, just like what we saw in the existing standards, we want to have a process assessment and a statistical analysis. So that would be some kind of quantitative analysis of the model. Now, for this process assessment, we derive some requirements from existing functional safety standards, different white papers that have been published, and working group recommendations for machine learning, as well as just best practices in ML research. And then the statistical performance analysis that I mentioned is really based on the prior research that I did in my PhD thesis on a topic called network generalization prediction. And we're going to spend a portion of today talking about that in more detail. We're also pulling techniques from FMEAs and FMEDAs that we like to do in functional safety. So first, with the process assessment, what we've done as exida is gone through and began to identify additional requirements that we want machine learning models and the folks developing these models to meet. We've done this by identifying key criteria, and then underneath each criteria, additional requirements that we want to add to the existing standards. And the goal of these additional criteria is to really ensure that the model, the ML development process and the model itself is safe throughout the engineering safety lifecycle. And here on the left, I'm showing just our illustration of what a safety lifecycle V model would look like for machine learning. One example of what this could look like is in the specification stage of the ML model, specifying the intended operating domain, specifying different requirements for different use cases, and then tracing those requirements to specific training data where the model should be learning to perform correctly in different conditions, as well as test cases, to make sure that the model is meeting those requirements. So that's one example of what this could look like for a machine learning development process. Now, as I mentioned, we've developed these criteria, and so there are 10 of them that apply to both the ML developer, that's the group that's training or designing the model, and then the ML integrator, the group that's taking a model that's been designed and integrating it into a larger system. And there could be cases where the ML developer and the ML integrator are the same group, but that's how we're breaking it up right now. Okay, so we've talked a little bit about the process analysis. Let's talk about the statistical analysis. So we talked about the process assessment, and that piece is looking at, how was the model designed, how was it specified, you can imagine this being, was the training code for the model generally correct? And so a lot of that can also pull in requirements for existing software. But a challenge that isn't going to be addressed with existing software is answering the question, did the weights that I learn, are they able to solve the task that I want them to solve? And so that piece of, have I really learned good enough weights, is what we're going to address here in this ML statistical analysis. So like I mentioned earlier, this is based on the work that I did on network generalization prediction in my PhD. I will also say, there could be a number of ways that you could try and analyze an ML model. What I'm going to present to you today is right now how exida is thinking of solving this. And so with network generalization prediction, the goal is to be able to predict how well a model will perform in a new operating domain based on tests that you have performed. Okay, and so this can help you understand if the model performance is good enough for a safety critical task, where it's safe to use the model, and what the likely failure modes of the model are going to be. So here in this picture, I've just got a bit of a flow diagram of how this works. So you can imagine you have some architecture, and that means a setup of how the model, what's going on inside of the model. And for that architecture, you need to learn the parameters inside called the weights. So you have some training data, you go through this process and you update these weights. And then at the end of the training, you're going to test the model, okay? So the idea of NGP is from one set of test data, we're going to find patterns in the model's performance and then use those patterns to predict how well we're going to perform in different types of operating domains. Okay, so we're going to go through this in more detail, but that's just a high-level picture. I have a number of publications in this area. 2 of these were done with funding from exida and with collaboration of exida. Okay, so let's talk some more about network generalization prediction. So there's 3 steps to summarize what we're going to be doing. The first step is we want to test throughout the intended operating domains. Then we're going to identify patterns in the ML performance. And then finally, we're going to leverage those patterns to predict how well the model will do in a new operating domain. Okay, so here on the right, I've got an illustration for an example perception system. The idea is we've defined that, or we found that the time of day and the weather could impact the model's performance, okay? So those are being shown here, time of day on the vertical axis and weather on the horizontal axis. Then we've taken this operating domain and split it into partitions, where each of these squares corresponds to one local context. And here, this X is pointing to this square, which corresponds to, let's say, a partly cloudy weather and maybe mid-afternoon, time of day. Okay, so each of these squares corresponds to some context that is understandable, interpretable. You can understand what this means. So first, we're going to take our model and we're going to run a number of tests. Okay, so here the circles are representing your tests, and the color corresponds to the outcome of a test. So anything in green means the model worked as intended. Yellow circles mean the model had a safe failure. And then a red circle means there was some kind of dangerous failure. Okay? Then what we want to do is identify patterns in the ML performance. So since we partitioned the operating domain into small contexts, we can go one local partition at a time and understand the average model performance in that context. So you could imagine getting the average failure rate of the model in one of these contexts, or calculating the average probability of success or failure. So however we want to do it, we're going to talk about what the model performance is like in each of these contexts. And then once we've done that, we can leverage that to make predictions. So I know there's a lot going on in this slide. The idea is this large square that we talked about as the operating domain is sort of the set of everything that the model might run into. Within that space, there are different distributions of the likelihood of those contexts. And one of those distributions you could imagine being like one user, one driver of a car with an autonomous driving system. So this probability distribution is then going to be for one specific operating domain. And what you can do is weight the average performance you saw in testing for each of these contexts by the likelihood of encountering that context in operation, and then that gives you a targeted prediction of the failure rate you'll expect for that particular usage situation. And so that's what this equation here is talking about. And part of the power of this is it lets you make a number of different predictions based off of just one set of test results. Okay. Now, you might be thinking to yourself, okay, I mean, that's great, Molly, but you're showing me this diagram of two axes where you already know what the features are that impact the model performance. But we just talked about in the beginning of this talk that we're only going to be using machine learning in complicated tasks that we can't solve with any other technique. So how are we actually going to practically do this for a complicated task? Oh, I'm so glad you asked. So yes, exactly. That is a very valid question and concern. And this is one of the things that we addressed in my prior work. So the idea is often for complicated tasks, there could be a number of factors that might impact the model's performance. And typically, you're not quite sure which one has the biggest impact. So what we did is we defined an algorithm that can look at your test results, look at the set of possible features that might impact performance, and then rank them so that you can understand which of those features has the biggest impact on performance. And then also decide how many of these features you need to consider in your analysis. The way this works, just very briefly, is by using a metric called the mutual information. That's looking at how much information a given feature in an example gives you about how well the model will perform. So by leveraging this mutual information, we can get a small subset of the available features that really give a good prediction on the model's performance. And then once you've done this, it can help you understand, even for complex tasks, what's driving the model's performance, if the performance you currently have is going to be adequate for a safety critical task, in what settings it would be safe to use the model, and what the likely failure modes of the model will be. Now, at exida, we're all about safety, so the focus of this is really in a safety context. But I'll also just mention that this technique is of interest to folks even outside of a safety context. So in machine learning, you're often working with really large data sets, and it's hard to distill down from that large data set to understand what's impacting your performance. If I could collect some more training data, what data should I collect? If I could run some more tests, what tests should I collect? So having this technique to understand what's really driving the performance can be helpful even outside of a safety context. Okay, so there you go. So this is one technique that helps make this network generalization prediction practical even for large complex problems. Okay, so we've done our NGP, We figured out what drives the performance. We've done our tests. Now what we can do is, based on this quantitative analysis, we can understand in what settings it's safe to use the model, and in what settings it's not safe to use the model. So here in this example, I'm illustrating that with these contexts in white being potentially certifiable contexts, and then in gray being uncertifiable contexts. And one of the benefits of this technique is it lets you safely use a machine learning model without requiring that model to be perfect everywhere. And I think that's really important, because given the nature of how you train machine learning models and the weights are updated, even if you were in a case where you had infinite training data and infinite training cycles, which we know isn't really the case, there aren't guarantees that just by showing more examples, the model's performance will improve everywhere. So I think it's going to be important to understand how to safely use imperfect models in the settings where that's appropriate. Okay, so for the ML developer side, which is again the folks who are designing and training the model, we've talked about how you could do a process assessment and then a statistical analysis to lead to some kind of model validation. But once that model's been validated in the abstract, how do we take that model and use it safely in operation? So this falls then into the ML integrator side of this workflow. So let's talk about how you could safely integrate machine learning into a larger system. So one technique that we often see in this sort of integrating of large systems is a HARA, hazard and risk analysis. This is a systematic approach to identify different hazards and risks within a certain operating context. So in this, you go through and you quantify the severity of risks and hazards, and then you also define what a tolerable risk would be for your application. And generally in the HARA, you're considering things that would have a safety impact, but also things that could impact the environment and business and social aspects. So in the context of machine learning, going through the HARA, you can define if your model is going to be high or low risk for the given application. And that picture we were just looking at of the certified versus the uncertified context, using a model in an uncertified context is something that would put you in that high risk category. Now, if you're using the model in a high risk category, you want to be able to design safety functions. Now, safety functions are a standard technique in functional safety systems. In a traditional, let's say a process application, a safety function might be a pressure relief valve. So you have some process, you've defined a safe level of pressure, and if the pressure goes above that threshold, this valve opens, releases some excess, and the pressure goes back down to a safe level. So a safety function is something that will intervene in the presence of a hazard to keep the overall system in a safe state. Now, what would a safety function look like for machine learning? One example could be different maximum speeds for an autonomous driving system based on the road conditions. So in a clear day, you can drive all the way up to the safety or to the speed limit, but in snowy weather, that maximum speed is going to get dropped. A different example could be some kind of handoff between, let's say, a collision avoidance system using machine learning and a more deterministic collision avoidance system. So maybe in ideal conditions, the ML collision avoidance system has better performance, but if there starts being noise or interference in the sensors, you hand off to that more deterministic system. Now, I alluded to this just a few slides ago, ML verification. So this is where we want to ensure that the way we're using the model aligns with how the model was validated or certified. So here again, we're seeing this operating domain, and we have these white squares correspond to where the model was certified previously, and then these gray squares correspond to where the model was not certified. Now, this red square is indicating where the integrator wants to use the model. Okay, so in this verification step, we want to either ensure that we're using the model in the safe or certified context, or if we're using it outside of that, we have some additional safeguards that will keep the overall system safe. So one way that that could look is having safe operation inside of those certified contexts, but then an additional safety function in these uncertified operating domains. So again, that safety function could look like maybe limited capability, driving at a lower speed. Maybe there's redundancy in the sensors. So there will be different techniques that the integrator could use to make sure that you're keeping the risk at a manageable level throughout their operational context. Now, we all know things change. There's sort of a common thing that's seen in machine learning is, you train the model, you test it, it looks like your performance is very good, you start using the model, and then over time, the performance degrades. This is often called data set drift, and this can be due to gradual changes over time. A different but related case could be, the model coming across examples that it hasn't seen in training, and it wasn't really intended to be used for. So to address these types of scenarios, we're proposing to have continuous monitoring. And this would be ways to, in real time, observe how the model is making predictions and continually be confirming that the types of data it's seeing align to what was expected based on the training and the testing. So I have some previous work that could be relevant in this area. In machine learning models, often we're talking about a neural network, which is going to have a number of layers. And after each layer, there's going to be some kind of intermediate output. So by looking at the output of the second to last layer, let's say, what I found in the previous research is you can define regions in that what's called the embedding space. That's the sort of intermediate output space. And what you can see is patterns of if an input data sample maps in one region of the embedding space, that's often linked to having a correct prediction. Where if a different data point maps to a different area in that embedding space, that corresponds to a failure. So that's one sort of technique you could use where without requiring labels to the data coming into the model as you're using your autonomous driving car to be able to monitor if something appears to be correct, a prediction appears to be correct. There's lots of other really great research in this area. One of those fields is called error prediction. So that's something very similar. We're looking at either, that intermediate outputs of the model or let's say statistics around the output. You can predict if what the model is predicting will be correct or an error. And there's another area of research called out-of-domain detection. And so this is really looking to determine if an input or an incoming data sample aligns with the data that the model was trained with, or if it appears to be from a different sort of domain. And so these are different ways that you could do this continuous monitoring to detect either data set drift or incoming data that doesn't seem to align with how the model was trained. So if you put this all together, this is the picture for what exida is envisioning for our machine learning service offering. So on the ML developer side, a rigorous process assessment, including additional requirements that exida designs, and a statistical analysis to confirm that the model can perform its intended tasks within certain specified conditions. And then on the integrator side, a HARA, designing ML safety functions if needed, then an ML verification to confirm the model's being used in an appropriate setting. And then after the model has been used in operation, some continuous monitoring to confirm that the way the model is working in the field aligns with what we expect. I also put this other box here, ML advisory services. This is just to say that if you have questions or you need help with something that doesn't exactly fall into one of these boxes, please reach out to Exida. We can also provide help as needed, even if it's not necessarily in one of these steps. All right, so last, I've just got a few more slides on conclusions, and then I'll take some questions. All right, so, Exida, we're a knowledge company. We have offices all over the world, as you can see in this map. We've authored a lot of books on automation safety, reliability, and cybersecurity. We have an industry data handbook on failure rate data that informs our analyses like FMEDAs or SIL verification. And we have most comprehensive book on functional safety in the market. Working with Exida, we have 3 different branches. One develops engineering tools like Excellentia, one performs certification and assessment, and one does system lifecycle services. So we can offer you powerful engineering tools, a thorough certification and assessment schemes with a pragmatic approach, comprehensive system lifecycle services, as well as webinars like what you're watching right now, blogs, training, and courses. So, like I mentioned, we have lots of different offices. I work here out of the Sellersville, Pennsylvania office, but please feel free to reach out to us on the internet, over email, give us a call. We'd be happy to see how we can help you. So with that, I think that's my last question of the webinar, or my last slide. And now I can turn to some of the questions that you all have. So let me see if there are any questions. Okay, I see there's one here. Let me pop this out. Okay. So the first question, and I'll try and read these all out loud. Can you comment further on the increased process rigor required to manage systematic specification and validation issues to handle the less defined nature of the I/O relationships with AI systems? How do the 10 process analysis considerations compare to the 61508 Part 3 techniques and measures in the appendices? What additional rigor do they handle? Okay, great. And I'll also say that some of these questions we'll also send out some written responses. So I'll kind of give the answer now, but then also some of these things, if there's a lot of details, we'll write that out. So I think one thing to keep in mind is we're going to be using all of the existing standards that can apply to machine learning. So in this question, they were asking about different tables and the appendices of Part 3 of 61508. So I think anything that we can use to apply to machine learning, we're going to use what's already there. So we're only going to be adding additional rigor to that. We have gone through and done our best to define what these process requirements will be, but what our plan is to also perform some pilot ML assessments. Now, what do I mean by that? I mean working with customers to use our criteria and then say, hey, is this criteria we have, is it rigorous enough? Do we need something more? Or is it not really possible to meet this requirement and maybe here's a different one that we can use? So we're planning on having this kind of intermediate period. And then I'll also say within Exida, we're planning on having a lot of sort of friendly discussion and debate to make sure that, across our international team, folks are aligned and agree that we're performing this with enough rigor. So, I think that's a great question. I think we have to start somewhere. So that's our intent. And I think also going through the process of brainstorming, okay, what are the features that could impact the ML performance? And then doing that NGP analysis and defining, okay, actually, you know what? We had 20 possible features that might impact performance. We found here are the 5 that really do. That can then feed back into the process assessment and say, okay, we've now understood that these 5 features are really driving performance. So how do we make sure we have a rigorous enough specification of the operating domain using those 5 features? So that they can kind of work together, those 2 pieces. Okay, so I hope I answered your question. but I'll definitely think if there's more I can add in the written part. Okay, next question. How do you predefine the certifiable context and the uncertified ones? Okay, great question. So this isn't necessarily something that's been predefined. I think what we're going to see is for each product, you're going to have to define what's the level of performance that I need for this to really be a useful and a safe solution. So that might correspond to some failure rate. It also might correspond to some probability of success, So I think what we're going to do is say, okay, and actually I can go back to that slide. Let me just jump back to that slide for the moment. Okay, so here, really want, this is just an example, and so you'll see that I've really kind of defined the certifiable region to be where there aren't dangerous failures. But I think in practice, there's going to have to be some agreement, and I think at the beginning it's going to be project specific of what's the level of either failure rate or probability of success that we could actually use this model for, and then that's going to drive what these possible certifiable contexts will be. Okay, great question. Let's see, next one. What is happening at the ISO IEC standard level regarding use of ML AI techniques in safety systems, safety functions? Are there any upcoming standards? Yes, okay. So I know that they're working on an update of both 61508 and ISO 26262, and that there are working groups talking about how to address ML standards. This is all, still in that working group phase, so I don't think there's anything defined and public about what those requirements are going to be, but they're definitely working on that. And I expect we're going to hear some things in the next year, and I think definitely in the next couple of years, it's going to start, seeing a clearer picture. Ari, slide 26. Okay. I think maybe that was this slide. That was just related to one of the other questions. Okay, great. Can you speak to the impact of the new EU machinery regulation and the new AI law regarding the use of ML AI in safety systems? Yes, okay, I had a colleague send me this. I looked at it very briefly. I didn't look at it in a lot of detail, so I might have to get back to you with a more specific answer in writing. My memory is that this was more on the legal side, but definitely I'm going to follow up with you on that question over email. Okay, next question. Can you point to an example where this methodology has been successfully applied? Great question. So I'll talk, this is in a research context, so let me talk to you about the examples that we looked at in research. We looked at pedestrian recognition using faster RCNN, and so we looked at both. Actually, let me go to just if you're interested in looking up the papers. Okay, so I can just kind of point you here. This first paper was really where we defined the math and the methodology, and the example here was a simulated example with a small network and a task where we performed reinforcement learning to sort of control something in simulation. So this is more of a simulated example. This next paper here, network generalization prediction for safety critical tasks in novel operating domains. This paper was where we looked at, okay, can you take a complex, large neural network, so faster RCNN for pedestrian detection, and use this type of methodology to predict how well the model will perform in different types of scenarios. And we found that, yes, you could. And so that is also the paper where we talk about, I mentioned this algorithm to take a complex problem and then identify what of the features are driving performance, and then do that network generalization prediction based on those features. So that algorithm is also in this 2022 WACV, that's the conference. You call that WACV paper. And we looked there. All right, I could talk all day about this, but so this one we're looking at pedestrian detection, or not, pedestrian detection as an example. The other case that we've looked at is for melanoma classification. And so that was where we had a model for melanoma classification. And what we found was actually that ranking algorithm to understand what features impact the model performance, that helped us realize that the model hadn't learned a good rule, let's say. So that was also interesting. This last paper, it talks about when I mentioned looking at where an input data sample maps in that embedding space and how that can give you information about if something is likely to be a correct or incorrect prediction. If you're interested, that's what this last paper is. Okay. So those are the examples we looked at. This last paper, we looked at a number of different image classification problems. One was on whether an image patch had a pedestrian or not. One was on melanoma. One was on general animal detection. And there's a number of different data sets that we use. So you can look at that paper if you're interested. Okay, next question. What do you believe is the max realistic achievable SIL level using this method? So that's an interesting question. I think in isolation, it's hard to say. And why do I say that? Let's imagine one scenario where you have one neural network trained on one test data performing a task. I keep coming back to pedestrian detection, so let's just say that. Okay. Now let's imagine a different scenario where you have two different architectures trained using the same data perform the task, but there's differences in the architectures of the model. Then let's think about a third scenario where you have two architectures trained on two different training sets. Okay, and when you've got two models, you're using them to check each other, you know. And then let's consider a third set where you have, you know, a computer vision model, you've got LiDAR, you've got radar, and you have these different diverse redundant sensors trying to work together on a task. I think just like what we see in the existing standards, as you start adding in redundancy at the final level, the level of performance that you can expect is going to go up a lot. If we're talking about one model alone, you know, in machine learning, to get 95, 99% is good, but in a safety context, that's not good. You know, we're talking about 1/5, one failure for every billion operating hours, or 10/5, one failure every 100,000 operating, 100,000? No, 100 million operating hours. So I think if folks are trying to just use one model, it's probably going to be challenging to get there. But as you start adding in diverse technology, redundant models, that might make this practical in, you know, safety critical tasks, and, you know, high demand or continuous demand safety critical tasks. Okay, here we go. Next question. Can you advise on how design time tools should be handled with respect to IEC 61508 T1, T2, T3 classification and their impact to the runtime code? Yeah, okay, great question. So tool classification, what do we look at? You know, can it impact the model at runtime, and you know, what that impact could be, how well defined are the different failures? You know, if you're thinking about something like, typically in machine learning, you're using a library. You know, you're not writing the backpropagation yourself. You're using some library to do that training. Typically, those libraries aren't going to be functional safety certified. So I think in general, I would expect you're going to be seeing some T2, T3 tools, and so that's going to have to be verified. I don't know if I can comment right now on how you would address that, but that's what I would be expecting, that some of these tools are going to be T2 or T3 classified. Yes, that's some great questions. Any other questions on this? free, you know, if you think of something later on, feel free to email me. My email is mobryan. Do I have it somewhere? Oh, I don't even have it on the slides. Oh well, my email is mobryan@exida.com. I think hopefully we'll send that out when we'll send out a report with some additional answers to these questions. But yeah, please reach out to us if you have any questions, and we're here to help.
Excellent. Thank you so much, Molly, for a wonderful webinar. And thank you, everybody, for the great questions that you've asked. This session was recorded, so you are able to view it again either on our YouTube channel or via our website. That will be published later this week. If you have any additional questions, please feel free to contact academy@exida.com, or you can email Molly directly at mobryan@exida.com. Molly will be getting a report of your contact information and the questions that you did ask, so she can follow up with you if necessary. And again, thank you so much for attending our Exida webinars.
Yeah, thank you so much. Have a great day, everybody.